In previous videos, we've been looking at a sequence of estimates based on derivatives, predictions into the future. We're now going to add some terminology around that and some mathematics. What we've been relying on in all of those examples was what we call local linearity. And the idea is if the function is differentiable at a point, so we have a slope, then that function behaves like a linear function for things sufficiently close to that point. Now, this is going to be a question of argument. Economists, biologists, everybody have debates about this when it comes to particular examples. But the fundamental idea is that if we have a rate of change, then we can use that to predict a little bit into the future or into nearby values of the inputs and get a reasonable sense of what's going to happen, with the smaller the change being giving us more accurate, with the caveat that smaller changes in the input tend to provide more accurate predictions in the output. From the graphical perspective, what this means is if we can zoom in on a graph at any point, if there's a derivative defined, then we're going to see things that look like a straight line. Let's see that in practice. For example, if we look at the essential wavy line of the sine of x graph like this, and if we carefully look at the scale on the horizontal axis here, what you see is initially a function that's not linear at all. Absolutely not. It's about as far away from a straight line as you can get. However, if we are to zoom in from around negative 1.5, so about here to here, and if we zoom in on that portion of the graph, we get this graph here. And there we see, all right, the tail end of that part, we start to see it looking less wavy, at least in this region. And then if we carve that off into an interval like so, and look at that region, well, all of a sudden, when we were zoomed out a long way away, we saw lots of waves, but if we are zooming in on this one point, we start to see things that look pretty linear. In fact, if we zoom in one more time, we're going to see a graph that essentially looks like a straight line. Here actually is a straight line drawn over top, and in fact, most of the ambiguity is from missing the point there. So this is a very straight line, and if we had this slope value and used it to predict into the future or to the right or to the left, we could get a very accurate prediction. Now it gets less and less accurate, especially if we go into larger steps where we get away from the linearity. But if we zoom in enough and take a small enough step, the sine function looks like a straight line. We can even go more exotic than that. Here's a function related to sine, except it has a 1 over x in it. And what that means is, as x gets closer to 0, we get larger and larger values in here. And what it means is we actually get faster and faster oscillations in the sine function. We're basically squishing all the oscillations that would happen in the right-hand side of the sine graph and packing them into the interval from 0 to 1. It's an exciting function. What we see, though, is even this function with the crazy behavior near 0, if we pick a point just a bit away from 0, and we zoom in, so we take a little interval here, and we see a pretty crazy function, but if we look at our point now and zoom in again on that, we see, oh, things are looking more and more normal, and even more than that, they're looking more and more linear. Because there is a tangent line I can define here, if we zoom in enough, we're going to see something that looks like a straight line. What does that mean for us? It means we can start to do meaningful predictions or formula calculations. So imagine we have a point here, and we knew the tangent line slope. So the slope of this line is equal to f prime of x. Now, of course, the function itself might deviate a little bit. Again, if we take the scale small enough, we might have our function that does something a little bit different. But on the scales we're interested in, this is going to be enough. And what we can do is talk about how our function changes and how that relates back to the formulas involving rise over run. So if we say we're going to take a small step in x, this little change here is like, it's almost the change in f, right? We have an exact value here, but the blue line and the green line are slightly different from each other, so this is an approximate value for the change in f. But that change in f over the change in x is then going to be approximately equal to the slope of that blue line. Well, that is exactly what f prime of x is. We often call this change, in the more traditional sense, delta y, though delta f is also possible. And if we wanted to use this system then to predict, what we've been saying is if we change x a little bit, how much does the function change by? Well, that's delta y. And all we do is rearrange. We just bring the delta x up to the other side, like so. And this gives us the motivation for our velocity times change in time, meters per second times meters. This is exactly the physics formulas that we typically use, but what we're seeing here is that it's a general relationship. Anytime we have a function and we can get the derivative, we can find the vertical change we get from a small change in the input using this formula here. And it's just rearranging the slope is rise over run formula and recognizing that we've got a straight line as our building block based on the slope. The actual curve may go a little bit differently for small delta x's, but if the delta x is small enough, this blue line and the green line will stay fairly close to each other, and this will be a good approximation if delta x here is relatively small. Here's that same expression simplified and rewritten in a way that brings in the derivative notation. Remember that our slope, written as f prime of x, can also be written in the Leibniz notation of dy dx, and that was designed specifically to harken back to delta y over delta x. Of course, this dy dx is our instantaneous rate of change, and this is an average rate of change because we have 2 points. And what we're saying is, yeah, if we're going to use the slope value, if we're going to extend that to a non-instantaneous rate of change, well, it's going to be an approximation. When we go to solve for delta y, we get the relationship we saw on the last page. And that's the essence of using derivative information to predict into the future. We have a certain change in our inputs. We multiply that by our slope to get the change in the output. With that, we can formalize the work in our earlier examples. We had our monthly revenue based on the amount of advertising. And if we had $200,000 as our current advertising budget and increase that by 2, well, that is a change in A. What we have is f prime of A is the change in revenue over the change in advertising. That's an approximation. It's exactly equal to the derivative. But what we're going to take advantage of here is the approximate relationship. And then we solve for the change in revenue. The change in revenue is going to be approximately f prime of A times the change in A. We have the derivative from earlier was 1.8 thousands of dollars in revenue per thousand of advertising. We were just told that the change in A is $2,000, and so we would get $3.6 thousand in revenue. And it would be an increase because this is positive. And we can do exactly the same thing. The change in revenue would be approximately equal to the slope or the rate of change times the change we make in our advertising. Here we have delta A being $1 million, which is 1,000 thousands. And so with the units given, we'd use delta A as 1,000. And we would get $1,800,000, which is the same as 1.8 million. And it would be an increase because that value is positive. So using this linearization idea and formula approach to it lets us do these kinds of intuitive calculations a little more explicitly using formulas that have some real underpinnings from the mathematics.